Okay, let's go ahead and take a look at maximum and minimum using trig functions. Now this is one question taken from the book. Basically it says that a circular piece of tin plate of radius 10 centimeters has three segments removed. So this part here is removed, that part there is removed, and that part there is removed. It says if theta is the measure of angle COB, which is that angle right there, show that the remaining area is given by A is equal to 50 times by the quantity theta plus 3 sine theta, and find theta to the nearest 1/10 of the degree when the area is a maximum. So what we're trying to do is we're maximizing this. So what happens then is that this can actually open up and down, and we're trying to make sure that this area over here, which is the shaded part, is actually going to be its maximum value. So the first thing that we have to do is we have to find out exactly what the shaded area is. Now, I went ahead and drew a couple of extra dotted lines here, right there, so that I can form a triangle here. I also drew another triangle here, knowing that this angle is pi minus theta, and it's going to be the same as that side there. So what I have then is as my initial statement, here's my initial statement, is that the area of the shaded part is going to be the area of this sector here, because that's going to be a sector, plus the area of two big triangles, so that triangle there and that triangle there, of course they're going to be exactly the same in terms of its area, plus the area of the smaller triangle at the bottom here. Now what this means then is that we actually have to go back and we have to think, okay, how are we going to actually find out what the area of a sector is in radians, and how do we do that also with triangles? Well, remember that whenever we have theta being in radians, we can go ahead and say that the area of the sector is going to be equal to 1/2 r squared theta, and the area of a triangle is just going to be 1/2 AB sine C. So what we can do then is we can just go ahead and start putting in some of the values. For the area of the sector, we have 1/2 times it by the radius, which is 10 squared, times it by theta, which of course is in radians, plus 2 times the area of the big triangle. Well, the big triangle is going to be this side here. Well, we're going to have 1/2 AB, well both of those are 10, times it by the sine of this angle here, plus the area of this small triangle here, which is going to be 1/2 10 times 10 times it by the sine of theta. Okay, and there you go. So once we go ahead and simplify all of that, this just becomes 50 theta plus 100 sine of pi minus theta plus 50 sine theta. Now what we're going to have to do after that is we're going to have to look at how to actually simplify this, because I don't know exactly what that is actually, what that's equal to. But if we go back and think back to when we were dealing with the unit circle, remember that if we go ahead and call this pi, this theta, this angle theta, then of course that point on the unit circle is actually going to be cosine theta comma sine theta. Now if I go ahead and draw the same angle on the opposite side here, then what we're dealing with then is this angle that starts from the positive x-axis and goes up to here, and that's actually going to be pi minus theta. So notice that this coordinate here is going to be cosine of pi minus theta sine pi minus theta, and notice that the y values are going to be the same, so we can say that sine of pi minus theta is the same thing as sine theta. So what that means then is that we can simplify this equation here to 50 theta plus 100 sine theta plus 50 sine theta. Now we can add these two here to 150 sine theta, and we can factor out a 50. So that means that we'll be left with the quantity of theta plus 3 sine theta, which is what the equation is in the book. Now, that is going to be the area of the shaded. Now we want to try to maximize that. So in order to maximize that, we have to find the first derivative. So the area prime is going to be the same thing as the derivative of the area with respect to theta. And so this is going to be 50 times pi, well the derivative of this theta with respect to theta is just 1, plus 3 times the derivative of sine theta, which is just going to be the cosine theta. Now of course, since we're looking for a maximum, we want to let the first derivative be equal to 0. So we solve for that, and we say that the cosine of theta then is going to be equal to negative 1/3. Now when we go ahead and take the inverse cosine of negative 1/3, remember that we're dealing with radians. This is going to be 1.91 radians. Now, that's what this is what our stationary value is going to be. The stationary point's x value or theta value is going to be. But what we need to do now is we need to check whether or not that is actually going to be a maximum or minimum. So let's just go ahead and use the first derivative. And if I was to just go ahead and say, for example, put in the value of 1 into the derivative here, then what I come up with is a value that's greater than 0. Now, of course, use your calculator for this. And if I go ahead and choose a value, say, for example, 2, then I come up with a prime going to be less than 0. So what I have then is a prime is actually going to go positive, 0, then negative, which means that the function for the area is increasing, maximizing, and then decreasing. So what I know then is that this value here for theta is actually going to be a maximum value by the first derivative test. So what I can do then is, being that the question is actually asking for the nearest 1/10 of a degree, I need to just change this 1.91 radians to a degree measure. And I do that by just multiplying by 180 degrees divided by pi radians, and I come up with 109.5 degrees. So there you go. That's how we can then go ahead and use trigonometry to solve problems that involve angles and finding maximums and minimums using all of the techniques that we know with regard to calculus. So give it a shot. We'll see how we can do, and we'll take a look at some problems together in class. All right, give it your best shot, and see you later.